Welcome to CH225 course on Statistical Data Analysis for Chemists. I am your instructor, Anil Kumar. These are my contact details. This is video 6 in this series. In this video we will learn about distributions. We will first learn about the distribution of discrete variables. In this, we will look into the frequency distribution. I recently purchased a bag of plain M&M. The M&M were in 6 different colors. A quick count showed that there were 55 M&M. Out of these, 17 were brown, 18 red, 7 yellow, 7 green, 2 blue, and 4 orange. These counts are shown in this table. This table is called a frequency table and it describes the distribution of M&M color frequencies. Not surprisingly, this kind of distribution is called a frequency distribution. Often a frequency distribution is shown graphically as shown here. The distribution shown here concerns just my one bag of M&M. You might be wondering about the distribution of colors for all ever produced. The manufacturer provides some information about this matter, but they do not tell us exactly how many of each color they have ever produced. Instead, they report proportions rather than frequencies. This distribution shows these proportions. Since every M&M is one of the 6 familiar colors, the 6 proportions shown in the figure add to 1. We call this a probability distribution because if you choose an M&M at random, the probability of getting, say, a brown M&M is equal to 0.3, the proportion of M&Ms that are brown. Notice that the distributions in these two figures are not identical. One portrays the distribution in a sample of 55 M&Ms, while the second shows the proportions for all M&Ms. Chance factors, involving the machines used by the manufacturer, introduce random variation into the different bags produced. Therefore, most of the individual bags will have a distribution of colors that is different. It should be noted that the variable color of M&M used in this example is a discrete variable. This is because color can only take certain values. Therefore, its distribution is also called discrete distribution. Let us now extend the concept of a distribution to continuous variables. The data shown in this table are the times it took one of us to move the cursor over a small target in a series of 20 trials. The times are sorted from shortest to longest. The variable time to respond is a continuous variable. With time measured accurately, to many decimal places, no 2 response times would be expected to be the same. Measuring time in milliseconds is often precise enough to approximate a continuous variable in psychology. As you can see in table, measuring responses this way produce times, no 2 of which were the same. As a result, a frequency distribution would be uninformative. It would consist of the 20 times in the experiment, each with a frequency of 1. The solution to this problem is to create a grouped frequency distribution. In a grouped frequency distribution, scores falling within various ranges are tabulated. This table shows a grouped frequency distribution for these 20 times. Grouped frequency distributions can be portrayed graphically as shown here. The labels on the x-axis are the middle values of the range they represent. This kind of graph is called a histogram. The histogram shown here portrays just response times in of the one experiment the person performed. To represent the probability associated with an arbitrary movement, which can take any positive amount of time, we must represent all these potential times at once. For this purpose, we plot the distribution for the continuous variable of time. Distributions for continuous variables are called continuous distributions. A continuous distribution is shown here. They also carry the fancier name probability density. Some probability densities have particular importance in statistics. A very important one is shaped like a bell, and called the normal distribution. Many naturally occurring phenomena can be approximated surprisingly well by this distribution. It will serve to illustrate some features of all continuous distributions. An example of a normal distribution is shown here. Do you see the bell? The normal distribution doesn't represent a real bell. However, since the left and right tips extend indefinitely, we can't draw them any further, so they look like they have stopped in our diagram. The y-axis in the normal distribution represents the density of probability. Intuitively, it shows the chance of obtaining values near corresponding points on the x-axis. Normal distribution is going to be one of the central themes of this course. Therefore, we will revisit this again in later videos to understand more features of this distribution. Distributions have different shapes. They don't all look like the normal distribution. The normal distribution shown here is symmetric. If you folded it in the middle, the two sides would match perfectly. Since we only have one maxima in this distribution, it is referred to as a unimodal distribution also. One can have a distribution, which is a combination of two normal distributions. It will have two maximas instead of single, as in a normal symmetric distribution. This is called a bimodal distribution. Similarly, we can also have multimodal distribution, which is nothing but a combination of many normal distributions, of different shapes. It is also possible that the probability density is not symmetric, but the tail can extend much more in the positive direction, as compared to negative. These distributions are called positively skewed distributions. Similarly, we can have negatively skewed distributions, wherein the tail can extend more in the negative direction, as compared to positive one.